Francois, you're really you've advocated a lot for program synthesis. And I'm curious, as someone who like created Keras and is obviously like kind of a black belt in deep learning, how did you become like a proponent of program synthesis? And what was that like? How did that happen?
Right. Well, very, very early on, I was really fascinated by deep learning. And like many other people in the field, I thought deep learning was going to be able to do everything. So I thought you could actually use gradient descent as a full replacement for programming, right? That neural networks, under some conditions, could be Turing complete, and gradient descent was a good enough way to program them into doing whatever you wanted, as long as you could provide them with enough examples. And around 2016, there was a lot of research along these lines. 2015, 2016, like neural Turing machines, for instance, and the like. And around that time, I was working on a project together with Christian Zigedy at Google, and we were trying to use deep learning to do theorem proving, in particular to guide a symbolic theorem prover. And I was training models to interpret higher order logic statements. So I was training RNNs back then, right? Using Keras. I was training Keras LSTMs. And I had a very difficult time with it. And I tried many tricks, many kinds of techniques to address it. But the inevitable conclusion I was reaching was that no matter what you tried, the neural network would always try to latch onto statistical regularities, like statistical noise effectively, and would not be able to actually implement the parsing program I wanted it to implement. It just could not find it. This was despite the fact that, in theory, that program was representable with the network. It's just gradient descent couldn't find it. And so I was struck by that fact, and I started realizing that deep learning actually was a good fit for some kinds of problems, where you're doing effectively pattern matching in continuous space, but was not going to be able to do everything that you actually needed to involve discrete symbolic programs. And that if you wanted to create these discrete symbolic programs, there were better ways than gradient descent. And I think this is a realization that's been confirmed many times since. And nowadays we even have examples where you have a very simple algorithmic task, and you try to solve it with a transformer, and the solution to generalize is representable by the transformer. And if you initialize the weights of the transformer with the exact correct weights that implement the generalizable solution, and then you keep fine-tuning the network on more examples of the same task, the network will unlearn the solution and generalize, and will learn a different overfit solution. So this is very, very strong proof that gradient descent is just not the way to learn algorithms like this, that you actually need discrete search.
So I guess how much of that do you put into like the learning mechanism, right? So in that case, you're saying you started with the initial conditions being the correct solution and you unlearn. So how much of that is kind of deficiencies in the learning mechanism versus the representation? So we'll just, before you came, we were talking about kind of the advantages of like symbolic program, kind of classical program representations versus, more like neural representations, and whether there's a benefit of like hybrids or things which are just distinct from either of those, right? And so I guess thinking forward, do you think is it primarily like new learning methods, like new optimization methods, or new representations, or both, or something else?
It's a little bit of both, but the primary bottleneck is actually the learning mechanism. The primary problem is gradient descent is just not the way to learn programs. The representation as well, I think we need better representations. I think so. If you're faced with any problem that has a continuous structure, then vector spaces are the right data structure to approach it. And if you have a problem that is more discrete in nature, it's always possible to embed your discrete structure in a continuous space. But of course, you don't derive any benefits from interpolating or moving around the continuous space. So it is clearly not. It is possible to handle discrete problems with neural networks. It is clearly not an optimal choice. There are no benefits to doing so. In fact, it's just not very efficient. So the representation problem, I think, definitely is real, and that's a space where you can propose new ideas. But it's not the primary bottleneck. You could do, in principle, everything with neural networks if you had the proper learning mechanism. Even though for many problems, neural networks might not be the best fit.
MLST is sponsored by 2 for AI Labs. Now they are the DeepSeek based in Switzerland. They have an amazing team. You've seen many of the folks on the team. They acquired Minds AI, of course. They did a lot of great work on ARC. They're now working on O1 style models and reasoning and thinking and test time computation. The reason you want to work for them is you get loads of autonomy, you get visibility, you can publish your research. And also they are hiring, as well as ML engineers, they're hiring a chief scientist. They really want to find the best possible person for this role. And they're prepared to pay top dollar as a joining bonus. So if you're interested in working for them as an ML engineer or their chief scientist, get in touch with Benjamin Cruzier, go to 2forlabs.ai and see what happens.
Yeah, I mean, we and you have done some work like looking at kind of embeddings of discrete structures into continuous spaces. And I think, in some of the early work, I remember you were saying to me, we could try this, but all of the evidence you've seen so far is that even if you can encode it, it's just going to create this intractable surface to optimize, and so it's actually not worthwhile. Do you think this is generally true, or like what are the cases where there is some benefit of having a relaxation or an embedding of a discrete problem into a continuous space, and what are the cases where like that just doesn't work out for whatever reason?
It seems helpful when you can prove that the relaxation is like actually kind of upper bounding what you want. So it can give you some guidance, because in the smooth space, there can be stuff that you can pretend to do that you couldn't actually do in the discrete space, but only as a kind of a stepping stone to refining into a discrete solution, which is kind of connected to, but I think distinct from using neural networks as a heuristic to guide discrete searches. But it is this weird empirical fact that when you try to train neural nets to like emulate algorithms, they just don't do it. Whereas they emulate all sorts of other interesting computations. It's really weird.
Yeah. I think it really depends on the intrinsic structure of your problem. If you have a problem that has a continuous interpolative structure, so a problem that follows the assumptions of the manifold hypothesis, then sure, you should be using neural networks. It is probably the best fit. If you have a very discrete problem, like I don't know, you want to find new prime numbers, for instance, you absolutely cannot use neural networks. It's just a terrible idea. So we've been talking about continuous representations, discrete representations. What do you think could be a hybrid substrate? A kind of data structure and kind of learning process that would not quite be continuous in nature, like neural networks, not quite be discrete in nature, like discrete program search, something in between that could do both at the same time. Not quite hybrid in the sense of combining neural networks with discrete search, but something hybrid in the sense that it is this one data structure that natively has characteristics of both.
Yeah. I think this is the big question. I don't think we necessarily have the answer. I think there are ways of, it still may come under hybrid, but I think there are ways of integrating neural networks into programs at a deeper level than what is currently being done, right? So right now, you've got programs calling neural networks and neural networks calling programs effectively. But I think there's a way to integrate, let's say, a neural network more into the semantics of a programming language, which could at least be interesting. So one kind of mental model I have in my mind is of debugging, right? So imagine you've got a Python program, and instead of just running it, you're debugging it, right? And so, more or less you're stepping through every kind of step of the execution trace. And at every step you can inspect the stack, you can maybe go backwards and revise the steps you did. What if you put a neural network there, right? Where it can actually control the dynamics of the program's execution. So this is a more deep integration of a neural network than just a black box function call. And I think it could lead to almost the program being the guardrails or the structure of how the thing should execute, but the neural network has more latitude about exactly what to do when. I think for a more bottoms up, reformulation, I think we need to think deeply what do we want from our representations of programs, and maybe my more concrete answer is to maybe take like a functional perspective, right? So you can imagine using a neural network to implement the operations that a kind of essentially to implement the interpreter of a program, right? And this is saying, well, I don't care about the underlying syntax, how this represented. I just care that when I execute this, I get the actual right result, right? And I think there's a lot of work that I've done like experimentally and other people have done saying, well, let's take a kind of a functional perspective. Like what do we want our programs to do as opposed to what they are? And if we know what we want them to do, then we can encode neural networks that implement those things. And that could perhaps make the learning problem, like the discovery problem of these programs a little bit easier, right? So this is like less, you were talking about neural Turing machines, and around the same time, there were things like neural stacks and neural data structures. This is less like, let's make a new architecture for this new thing. Let's instead perhaps use a standard neural architecture, but implement, a Turing machine or a stack by a kind of behavioral equivalence instead of like a structural equivalence. And so it's a little bit fuzzy, but I think there's a kind of a scope of approaches which are looking at a higher level of behavior rather than like new architectures. Do you have ideas about this?
No. First, I think it is the big question, as you were saying, to do what you're suggesting, like to make something which is more deeply integrated and not just a Frankenstein like bolting together these pieces. If we were to have a neural network that was executing the code, it might have the advantage that you could do some of the like test time training that we're seeing working on ARC, because you can kind of fluidly redefine the semantics for each problem. So this seems really valuable to be able to not just have like a fixed set of symbols, but to say like, well, for this problem, I want to like define what an object is a little bit differently, and it might be more of a perceptual subsymbolic thing. And if you were to define your semantics in terms of these neural operators, which had kind of the API of a programming language, but might have a subsymbolic implementation, then maybe you could get kind of the best of both worlds.
Do you have any ideas?
Yeah, I mean, these are very interesting ideas. And trying to learn a program interpreter, I think that can have lots of useful applications. In particular, even if you're just doing, discrete program search, you could leverage a neural program interpreter, because program execution is really what takes a lot of time in program search, right? And the forward pass of your program interpreting neural network would probably be quite fast. So you could use a neural network as a sort of guessing machine with respect to program execution, right? You're kind of like reading the program or some representation of the program and guessing what the behavior would be. And that would be a way to guide the search process more efficiently without having to actually, enter this execution loop.
One question I've had for you is, how important do you think are almost like systems level engineering problems or approaches in this? And I think about that in the context of your work in Keras and so on. And we discussed it a little bit over email, right? There's a whole ecosystem of machine learning built upon a framework of automatic differentiation, and then as you've built in Keras, layers on top of that. So as you think about like, these kinds of problems, these kind of high level problems, do you think we need like more infrastructure to support them? Or do you think we more or less have like the right foundation in order to tackle these?
I really don't think we have the right foundations today. I do think we need a lot more and a lot better infrastructure, and that will come. But I think right now we're actually at the research stage where we need to figure out what works. Like the state of program statistics today is pretty much the state that deep learning was at around like 2011, for instance. There's a lot more interest in it. Some things are starting to work, but we are still missing the big breakthrough moment and this sort of like crystallization of our understanding of what techniques are actually going to work and what techniques are actually going to scale, right, to solve real world problems. And once we understand that, once we've settled on one algorithm, right, then we can start building up infrastructure around it. And in the future, there will be a Keras for program synthesis, I'm quite sure. I don't think today is the right time to build it because we just don't know enough about the state of the land, basically. But in a few years, hopefully, yes, we're going to have that.
Yeah, so my main PhD advisor, Armando Soler-Lezama, his kind of main thing was program synthesis, right? And he's kind of the original program synthesis guy, joint with Kevin. Well, he advised us he advised both of us. And there was like a kind of a lot of different techniques for program synthesis that were developed, mostly symbolic. But symbolic doesn't just mean like, searching over programs. There's a lot of more interesting techniques, right? You can use abstraction, abstract interpretation, SAT solvers, SMT solvers, which are incredible pieces of technology. And then, language models came along and they started to generate programs, right? And in some sense, like the whole research paradigm was validated because it turns out that program synthesis is indeed very useful, but a lot of the methods that were developed aren't directly leading to like the current leading program synthesis methods, which are largely LLM based. And so I wonder, like, when you think about, I guess, current, technical foundations, do you think we're going to see a revisit back to some of the more classical techniques? Maybe classical isn't even the right word, but like methods which incorporate more of like the semantic understanding of what programs are, right? Which do more analysis versus things which are more kind of purely, data-driven, learned, even if they are using programs as the underlying representation that's being constructed.
I think the future is definitely more learned and more data-driven, but I think you can learn in a more symbolic manner. You can learn symbolic abstractions via a symbolic search process, right? I think the reason why people are using LLMs so much for code generation today is just because it works and it's easy. It's a tool that's available. The reason it works so well is just because of scale. Like the amount of resources that went into developing these models and training them is roughly, 10,000 times what went into the symbolic techniques that you're describing, which remain today very, very obscure academic topics. And meanwhile, there's like hundreds of billions of dollars that went into developing these huge models trained on all the code in the world. And when you put this amount of resource into something, even if it may not be the optimal approach, even if it's actually severely suboptimal, it will create something useful. It will create something powerful. And once it's out there, then you kind of have to use it. If you're not making use of it, you're just leaving, a lot of power on the table. You're just missing out on a very, very powerful, very useful tool. And so from a game theory perspective, it's just the sheer amount of investment in LLMs kind of forces everyone to standardize on this set of techniques, at least for now. Right? I don't think it's the best way to approach problem synthesis, but it's a way that is giving good results today. So it's just worth pursuing it.
Yeah. I one thing I wondered is like, imagine what like program compilation would look like if you used like GPT-4 level compute to compile your programs. Do you have any thoughts on this? Like,
I don't want GPT compiling. Like maybe it could write part of the compiler.
I just meant the level of compute, right? If you think about like how much compute goes into analysis of programs at the moment, it's it's like we get tired if we've spent a few minutes right on a single machine, right? If you had a cluster, a supercomputer, it expands the class of analyses and methods that you would employ.
Oh, like a super optimizer. Right. Yeah. I mean that could happen. Yeah. Probably hand in hand with the LMs, just because they're so useful in practice. So speaking of like scaling methods, are either of you freaked out by the fact that things like Psych tried hard to scale symbolic knowledge, and then today we don't use Psych, but we do use GPT? Like, how do you reconcile that?
Psych was never very, very scalable because it was very reliant on human labor.
I see. So you think learning was really just the missing ingredient?
So to scale, you need to be able to delegate everything to the computer. There should be no human in the loop.
Yeah, and I think also, there's a class of approaches which have been human-made ontologies of knowledge, right, by groups of dedicated people, and decade-long projects. And I think these have been, they've scaled in the sense that they've grown, but not, comparatively to, let's say, learning-based approaches. And I think part of the reason is what Francois said, like, you want to delegate as much as possible, if not everything, to the, to things at scale, computers. But also, classical ontologies are like just not good representations of knowledge, right? Like the world is not encoded in graphs. And so we need both like things that can capture the complexity of the world, and we need systems that can scale to build that knowledge from data.
Yes, and you can definitely, argue that vector spaces and embeddings are intrinsically a much better representation of knowledge than graphs. It may not necessarily be true for every type of data, but for most of the data that we care about, it is. And this is why neural networks actually do so well across so many modalities. They're just a fundamentally good idea compared to ontologies.
But also, I feel like there's a few different layers there, right? So there's the vector space, which is the most grounded layer, or in which things are encoded. But on top of that, there's whatever the learned representations to encode that. So I guess when you were speaking, I was thinking there's not, in my mind, a direct analogy between the kinds of graph ontologies that people have constructed and the vector space representation. They seem to be at like slightly different levels of implementation. I guess I've got some questions about ARC and your findings from the ARC challenge.
Oh.
I'm sure you'll talk more about this soon. Maybe could you just say like what was like kind of the biggest insight that you learned, or things that are unexpected going through the whole process of this most recent?
Right. The biggest insight is that I've come to realize that it's definitely possible to make LLMs and deep learning models in general adapt to novelty, and there's more than one way to achieve this. And test time training is definitely, it has emerged as one of the big techniques that are working today to get LLMs to adapt to novelty. It's still an open question whether test time training is actually good enough. Like, is test time training going to be able to do everything to solve strong generalization in neural networks? I think it's possible, with further refinements. And test time training is not even the only approach you can take. You can also do things in the style of the O1 model, where you try to adapt novelty by writing down a program, and that program is written, step by step in a very iterative fashion. In fact, it's written by an AlphaZero style search process, probably. And by writing down this program, which is an artifact that is new and is adapted to the task at hand, you can make your static model adapt to novelty, right? And a few years ago, it seemed to me that we were never going to get deep learning out of the classical paradigm, where you're just training a big model on a lot of data, and then you're applying it in a static fashion at inference time. And of course, if you stay within that paradigm, then you're fundamentally limited to memorizing and then at inference time fetching and reapplying patterns. And if you're doing this, then you're never going to generalize very well. You're always going to be limited to situations that are very close to what you've seen in the past. But now, if you include, test time fine-tuning to adapt to new patterns, if you're including the ability to iteratively write your own program, reprogram yourself on the fly to adapt to a new task, and so on, then maybe these systems can achieve a much higher degree of generality. And starting with cracking ArcAGI, I think it's highly plausible at this point with the early data points that we have.
Mm-hmm, mm-hmm. Do you see like a clear delineation between classes of novel, like things that are more genuinely novel and things which are not, right? And so in the past, you said one of the just like technical implications of encoding, your knowledge within a vector space is that you're really going to be, interpolating between, as you said, patterns of patterns or programs. But one of the things that ARC tries to test for, at least as in my view, is like a certain class of novelty which goes beyond that. And we've thought about and talked about like what is that boundary of novelty. There's clearly some generalization that happens between, which you can interpolate between. And intuitively, when you look at arc problems, there's some which seems like, oh, it requires some new concept or some new idea that we haven't seen before. But it's hard to say here is like the strict boundary between these two different kind of classes of generalization, if there are two. I wonder if you had thoughts on that.
Yeah, I think what you're describing is compositional novelty, where you're taking elementary building blocks and recombining them together, typically via function composition, right? And this is something that transformers are really bad at. In general, transformers are very bad at function composition, broadly speaking. It doesn't mean that you cannot solve these problems with transformers. It means that you cannot solve these problems only with transformers, right? You need to add something. But if you put your transformer in a loop, for instance, you start being able to do, to be able to solve a much larger set of problems. So one thing we are doing right now is trying to understand which of the tasks in Arc are sort of like easy to solve without exhibiting strong generalization, and which ones actually do require a little bit more, and remain very easy for humans, of course, because humans have the secret sauce for generalization, and we don't quite know what it is yet. And so early next year, we're going to be releasing a new version of Dataset that is trying to carry a higher signal towards AGI. So basically require stronger generalization. So it's going to contain fewer tasks that are easy to crack via just brute force search, and more tasks that really require, that involve compositional complexity and really require strong generalization to solve.
Can you give any more hints about what the design decisions are which go to push you, like what is it, like a systematic process where you'd say, okay, this new candidate Arc2 problem does force us into strong generalization versus not, or is it more of an intuitive process where like you just know as a human designer?
It's a little bit of both. So the thing is that we don't yet have a crisp answer as to how humans perform strong generalization, or what would be a kind of task that would strictly require it and that would not be approachable at all via brute force. So we don't quite know. So we're looking at the results that we're currently getting. We're also looking at human difficulty data. And by the way, this is also a big novelty with Arc2, that we're actually getting all the new tasks solved by humans, by just random people that we're hiring, and we're getting them to solve our little puzzles. And that's how we know, first of all, we know that they're solvable. And second, we have human difficulty data available. Like we know how many attempts were used, we know how many people solve each problem and so on. And we can see how that correlates with AI facing difficulty as well.
I see. I guess I got a question for maybe both of you. So within this new project Mara that we've been developing and have launched, we've been both thinking about our own benchmarks and also existing benchmarks. Obviously, we've started working on Arc. But there's a question of, should we continue working on Arc, right? And I guess both Arc 1 versus Arc 2 as it comes out. And this came up in our discussions earlier with Tim of like how much of the approaches that were taken to Arc in the previous round were truly in the spirit of Arc versus we're kind of trying to just like get the best score. And I think I said that our approach was, I think, a little bit of both, right? We had some Arc hacks, right? But we also thought deeply about some principles. So maybe as a question to Kevin, and I'd like to hear your thoughts, Francois, of like, how much time should we dedicate the Mara project to Arc? And if not, what other things might we want to pursue that are not within the Arc framework?
So I think Arc continues to be a source of new ideas, and there's been a lot of progress on it, but it's also been amazingly resistant to people trying incredibly hard to crack it. So I think there's gonna be a good payoff in continuing to work on it. I think with Mara, the main thing we want to bring into the picture is the fact that you're not just passively receiving the data. You're trying to play with something, experiment with it, and in the spirit of Arc, build a model on the fly. but where it's your job to figure out what kind of questions you want to ask and experiments you want to do. So I think our plan here is to keep on doing ARC stuff and thing in the ARC sphere, but also to supplement it with new kinds of tasks that are ARC style, but with this more active learning.
To you, Francois, should we wait for ARC 2 or should we should we continue on ARC 1?
I think ARC 2 is starting to saturate, but of course, I think ARC 1 remains a very useful playground. So you don't have to wait for ARC 2. If you have ideas that you want to try, you can try them on ARC 1. And if they're good ideas, they will score well. And then you can try them again on ARC 2 when it comes out. And you're not going to have to wait too long, by the way. And, you know, I think the reason why you should continue working on ARC is it's like a micro world for a lot of these important problems regarding generalization and on-the-fly adaptation. And if you look at any other benchmark that features the same problems, you will see that it also involves a very significant amount of knowledge. So for instance, you could be working on code benchmarks, like software engineering benchmarks, and they do feature the same kind of problems, but because they involve so much specialized knowledge about programming and programming languages and code patterns and so on, it kind of gets in the way. And ARC is this very clean, very minimalistic micro world where there's almost no knowledge involved, just, you know, a few bits of core knowledge. And it's all about abstraction generation. It's all about the key problems. So this brings really, I think, a lot of focus on the questions that really matter.